All right, let's get started. Today, we're diving into an absolute cornerstone of orthopedic biomechanics, a topic that's basically a rite of passage for every trainee heading into the FRCS exam, the stress strain curve. Mastering this isn't just about getting a pass, it's about really understanding the why behind pretty much everything we do, from plating a fracture to choosing an implant. So let's build that understanding from the ground up. And hey, don't just take my word for it. The exam guides like Postgraduate Orthopedics are crystal clear on this. This is not a nice to know. It's a must know. It's one of those questions that if you absolutely nail it right at the start, it just sets a fantastic, confident tone for the rest of your Viva. It shows the examiners you've got the fundamentals down cold. So to make sure you have that consultant level answer ready to go, we're going to structure this explainer just like a perfect Vivo response. We'll kick off with the core definitions, stress and strain. Then we'll actually build the curve itself. After that, we'll see how it applies to our materials and to biology, connect it all to clinical practice, and then wrap up with the key buzzwords that you'll want to have right in your back pocket. Okay, first things first. Before you even think about putting pen to paper to draw a graph, you have got to define your terms. A sharp, accurate definition of stress and strain is completely non-negotiable. This is where you start. So, what is stress? We use the Greek letter sigma for it. And really, it's the internal resistance of a material to an outside load. Just imagine the material itself is fighting back against being pulled or pushed. It's normalized by area. That's why the formula is force divided by area. And that's a really key point. It's an internal, distributed force. And then we have strain, represented by epsilon. Strain is the material's actual response to that stress. It's the physical deformation, the change in its shape. Now, critically, it's a relative measure. It's the change in length divided by the original length. And because of that, it's a dimensionless quantity, no units. And now for the main event. In the Viva, they're going to ask you to draw and describe this curve. So let's break down exactly how to do it perfectly, step by step. First thing you do is take your pen and draw the axes. Don't rush this part. Label them clearly. The vertical y-axis is stress, and you should mention the units megapascals. The horizontal x-axis is strain, which, as we just said, is dimensionless. Honestly, getting the axes right is the first mark in the bag. And this is the shape you're going to draw. This one elegant curve tells the entire story of a material's life while it's under load. So let's break that story down chapter by chapter and explore each of its distinct regions. We always start in the elastic region. That's this initial straight line part of the curve. Here, any deformation is completely reversible. It's just like stretching a rubber band and letting it go. It snaps right back to its original shape. This straight line relationship is described by Hooke's law. And the slope of this line, that's hugely important. That's Young's modulus, and it's our measure of a material's stiffness. A really steep slope means a very stiff material. Right at the end of that straight line, we hit the yield point. You can think of this as the point of no return. As soon as you go beyond this point, any deformation that happens is permanent. The material has yielded to the force, and it is not going to spring back to its original size. So, once we cross that yield point, we enter the plastic region. In this phase, the material keeps deforming permanently. It starts to neck as it stretches out. The stress keeps rising until it reaches a peak, a summit. This peak right here is the ultimate tensile stress, or UTS. That is the absolute maximum stress the material can handle before it starts to fail. After hitting that UTS peak, the material really begins to fail, and the curve slopes down until you hit the final fracture or failure point. Now, here's a crucial takeaway. The entire area under this whole curve represents the total amount of energy the material can absorb before it breaks. And we have a name for that property. It's called toughness. Okay, so let's take this theoretical curve off the page and apply it to the real-world materials we are using every single day in the operating theater. This image brilliantly illustrates the two classic types of material behavior. Look on the left, you've got a brittle material, like a ceramic. See how there's almost no plastic deformation? It just breaks. But then look on the right at a ductile material, like a metal. It undergoes a huge amount of plastic deformation before it finally fails, and that means it absorbs a lot more energy. And here we can see how that applies to our toolkit. Metals are stiff and ductile. Ceramics, even stiffer, but they're very brittle. And then you have polymers, like the polyethylene in a hip replacement. They are much more flexible. See that low stiffness? But they can be incredibly tough. Each curve tells you exactly how that material is going to behave when we use it as an implant. Now this is where it gets really interesting. Just look at the numbers. Look at the massive difference in stiffness in Young's modulus. Stainless steel is up at 200 gigapascals, while our own cortical bone is somewhere around 15, maybe 20. This huge mismatch is the entire reason we talk about stress shielding. And look how much more flexible bone cement and polyurethane are. Knowing these relative values is absolutely key. Right, but we're not just implanting inert materials into a block of wood, are we? We're fixing biological tissues. And guess what? They have their own unique and much more complex stress-strain behaviors. You can see the comparison so clearly here. Cortical bone has that steep, straight-line elastic region. It's stiff, right? But now look at the curves for tendon and ligament. They start off with a much shallower slope. That tells you they are way more compliant, especially when you first start to load them. And that initial shallow slope has a special name. It's called the toe region, and this is a classic Viva question. This initial, almost flat bit of the curve for tendons and ligaments represents the wavy collagen fibers literally uncrimping and straightening out. It's only once they're all pulled taut that they really start to resist the load, and that's when the curve gets much steeper. And you absolutely cannot give a complete answer about biological tissues without mentioning these two properties. First, they are anisotropic. That means their strength depends on the direction of the load. Cortical bone, for instance, is way stronger in compression along its long axis than it is in shear. Second, they are viscoelastic. This means their behavior is time-dependent. Bone is actually stiffer and fails at a higher stress if you load it really quickly versus loading it slowly. So you might be asking, why do we need to know all of this nitty-gritty detail? Well, because it directly explains why our implants succeed and, maybe more importantly, why they fail. And this brings everything together into a crucial clinical point. Most of our implant failures are not single-event, massive overloads. They're fatigue failures. So if your fracture construct allows too much movement, that is, high strain, then the implant is experiencing high stress with every single step the patient takes. Thousands of repeated cycles of high stress just eat away at the fatigue life of the metal, and eventually, it breaks. So you see, understanding strain is fundamentally understanding implant failure. Okay, let's bring it all home. To finish your answer with real confidence, you need to be able to pepper it with the right terminology. This is what shows the examiners you have a real depth of understanding. Here's your final checklist, your mental cheat sheet. Make sure you can define and use every one of these terms correctly. Young's modulus for stiffness, anisotropic and viscoelastic for bone, the difference between ductile and brittle materials, be able to point out the yield point and the UTS, and define toughness as the area under the curve. You know, if you can even mention concepts like creep and stress relaxation, that just shows an even deeper level of knowledge. So we'll leave you with a final thought, a typical follow-up question you might get. How would this curve actually change for cortical bone if you loaded it under tension versus compression? Answering this forces you to bring together everything we've talked about, the shape of the curve itself, and that critical concept of anisotropy. Think about it. Thanks for watching.